Hi there. Welcome back to Chapter 1.2 from Stevens' Matrices, Vectors, and 3D Math. In this chapter we're dealing with matrix and vector operations and their properties. And at the end of the last video, the end of the first video for this particular section, I showed you how we can take a system of linear equations and convert that into a single matrix equation, right? And then I showed you that there's a command in MATLAB that will actually solve the system if there is indeed a unique solution. And so I want to demonstrate that first because that really is the most impressive thing, and we left with that, so I don't want to leave you hanging. Excuse me. Okay, so once we have this system down here, that system of equations, once we have that in matrix form, AX equals B, all I have to do is go to MATLAB and enter the matrix A and enter the matrix B, or the vector, the column vector B. Then I can get the column vector, the solution to this matrix equation, with this backslash command, right? And it'll just return some numbers, but those numbers will be the solution. So here's what I mean by that. I have MATLAB running right behind this here, and let me clear that. Okay, so all I have to do is enter the matrix A. So do A equals, and all vectors and matrices start with a square bracket, right? And so the first row in the matrix A is 1, 0, negative 3. You can put commas in there if you'd like, but you do have to put a semicolon in to indicate a new row. So the second row is 2, 2, 9, semicolon. Third row is 0, 0, 1, 5. And I close that out with a right bracket and enter. So there's my coefficient matrix A. Now I just have to put in that right hand side column vector B. So I'll set B equal to 8, 7, negative 2. Right? And close it off with the right bracket. Now, the problem is if you hit B now, it's actually a row vector. I can change that into a column vector by just saying B equals B transpose. And I could have just used that transpose piece earlier whenever I defined B. And the transpose symbol is just a single quote, right? It's right below the double quote in your on your keyboard. Okay, so just to see what we have A, we have B, right? A is a matrix of coefficients, and B is the column vector of right-hand sides. So if I want the solution to this system of equations over here, and now I put it in the form of a matrix equation, getting the solution is super easy. I do A backslash, not divide, but backslash B. And that's the solution. And it works every time there is a solution, a unique solution, it will give it to you. If there are infinitely many solutions or no solutions, it may or may not return an error. It may return a solution that is actually not a solution. So we'll get into more ways to determine how you differentiate between a unique solution and otherwise. But for right now, it works like a charm. It saves you a ton of work. And I promised I would show it to you at the end of the last video, so there it is. All right. And by the way, the way you read this solution is the first term here, that's x1. So x1 is 5, x2 is 3, and x3 is negative 1. Easy. Okay, so what we're going to move on to here is creating vectors in MATLAB. You just saw that, but I'll go over it again here briefly. So let me make some room so that I can see what I have here. Suppose I want to define a vector. I'll clear this. I can define that as V equals left bracket 2, 4, 6. That gives us a row vector. If I want a column vector, I just do V equals 2, 4, 6, and then I put the transpose symbol, which is just the single quote mark, an apostrophe, I guess, and that gives you the transpose. All right. So now I have V. If I want the second term in V, I just do V and then the parentheses 2. That gives me the second term, which is a 4. If I want the second and third, I can do second through third. That's a colon. All right. I get 4 and 6. And then I can actually replace values in there. So there again is V. Suppose I want that 2 to turn in. Suppose I want this 2 here to be a 0. I set V1, that's the first term in V, equal to 0. And I hit enter. It changed the first term in V to a 0. Alright, and now the other thing, this is an amazing thing about MATLAB. It does memory allocation, so you don't have to predefine how big this vector is going to be, right? So if I have my vector V, suppose I want to append another term onto there. I just do V4. Suppose I want to set that equal to 5. Now my vector is bigger, right? That's one extra term. By the way, the indexing, so a lot of you computer programmers might not like this. The indexing of a vector or matrix or an array starts at 1. Right? So if you put in V0 and you think you're going to get the first term, you'll get an error. If you want the size of that vector, you just type size, and that gives you the dimensions. It is a 4 by 1 matrix, making it a column vector. You can also create a vector with this command here. V equals 0 by 0.5 to 1. And that I just redefined V, but that just basically goes from this first term to this last term by steps of 0.5. So the semicolons here, or the colons, I guess, in MATLAB represent sort of 2, right, or by. So it's 0 by 0.5 to 1. Right. Okay, so let me go over to this file, vectors.m, right? And I'll just show you a few of the things that we can do with vectors. Okay, and I actually have that file right here. I'll make the MATLAB bigger. Open up this file, vectors.m. So there's that same file. It's available in the program repository. And so if I want to run, this is basically a program or a script. And so if I want to run it, I just go up here and I click the run command. Alright, oh, I have to change my folder. Okay, so there's a lot of stuff going on there. We even got an error at the end. So let's make sure let's see what all this did. So the first thing we did is we defined X, Y, and Z. Alright, so they should be in here. X, Y, and Z. Alright, notice Z, I put semicolons in between each one of the terms. That made it a column vector because a semicolon gives you another row. And if you want to access the second term in X, so X, if I want that second term, again, X2, giving me 4. If I want to get the length of a vector, so if I do length of X, that tells me how long that vector is. Notice, if you look at Z, it's a column vector. If I do length of Z, it still returns a single number. There's 3 terms in that vector. If I do size of X, it's a 1 by 3. Right? That means it's 1 row, 3 columns, so it's a row vector. If, on the other hand, I do the size of Z, that's a 3 by 1. That is a column vector. And here's some things you can do. Here you have X, here you have Y. You can take X plus Y, and that adds them term by term. You can take 3 times X, and that multiplies every term in X by 3. And then here's a really weird thing you can do. If you look at X, suppose I want to add 2 to every term in X. I can just do X plus 2. That added 2 to every term. It really shouldn't let you do that because the size of the 2 matrices are not the same. Right? For example, if you look at x and y, if you try to add them, oh, it works out fine because they're the same dimension. But if you look at x and z and try to add them, x plus z, you get an error. The matrix dimensions must agree if you want to add these to everything's a matrix in MATLAB. So the dimensions don't agree, so you can't add them. But for some reason or another, you can take x and add the number 2, and it automatically just adds 2 to each term. That's why I call it weirdo. In mathematically speaking, you actually can't do that addition, but MATLAB will do it for you. You can do the dot product of x and y, x, y, so we can do dot x comma y. Well, that does the dot product. That's 2 times 1 plus 4 times 2 plus 20 times 6. You get 130. You can also do this in terms of matrix multiplication, right? If I do x and I multiply it, that's with the asterisk, right, times y, I have to make y a column vector. So x times y, that gave me the dot product. Notice if I just tried to do x times y, it would not like that because the inner matrix dimensions do not agree, right? In other words, the number of columns in x has to equal the number of rows in y, and that's not the case. If I try to take x plus z, let's see, what else do I have on here? Oh, yeah, x plus z you can't do, x times y you can't do. So you're going to make sure you're being careful with all of this stuff in with these dot products and matrix multiplications. And so the next page in the book goes into all sorts of MATLAB commands and the syntax. And instead of going through all of these, I'm just going to open up the file matrices.m and run through a few of these instead. And this file, matrices.m, is available from the program repository. So let's go to matrices. We'll open that one up. I will clear this console. And if I run it, all that information will get compiled, right? So I'm going to clear that. And so the first thing is this display command just puts a message to the command window. If you look at M, you have that matrix. N is that matrix, right? And if you want the size of M, that gives you the dimensions. It's a 3 by 3. And if you actually want to assign those values, you can do R comma C equals the size of M. And that assigns, so now R has the number of rows and C has the number of columns. So let me see. We'll go back to our matrix M. Suppose I want the term in M that is in the second row and the third column. Second row, third column. Suppose I want to access that 6. I just do M, left parentheses, 2 comma 3. That's the index associated with that number 6. Right? If I want the whole column from M, I can do that with this colon. The colon does a lot in MATLAB. So if we look at M again, if I want that first column, I just do M, and this colon means all rows, first column, 147. If I want that first row, I do M, first row, all columns, and I get the first row. Now we'll do some operations. If you look at M and N, I can do M plus N, and it just added them term by term. Let's see, if I have M here, I can get the transpose of M by just taking M and doing that single quote, M transpose. So notice the row 1, 2, 3, the first row became that first column 1, 2, 3. Second row, second column, third row, third column. So it automatically does the transpose for you. You can do scalar multiplication. If I look at M and I multiply 2 times M, it multiplies every term in the matrix by 2. Now if I take m times n, that does the matrix multiplication. That's nice because that's a whole lot of multiplying and adding over and over and over. It's what a computer is really good at. It's what we as humans tend to make errors on from time to time. And so notice m times n gives me this answer here. If I were to switch that around to n times m, it's not the same thing, right? So that's one of those key points from the last video. Matrix multiplication does not commute. When you switch the order, it changes everything. Sometimes you can't even do it. And you can do that weirdo operation again here. Suppose I have m. If I want to add 2, or say 5, to every term in m, I can just do m plus 5. It's convenient. Mathematically speaking, it's impossible, but MATLAB will do it to you. So I hit enter, and it adds 5 to every single term in m. Let's see. So now if I go to y, that is this row vector. If I try to take n times y, I'm going to get an error. That's because the number of columns of n does not match the number of rows of y. There's only one row in y. So I have to remember to do n times y transpose. And that works out just fine. If I want to solve this linear system ax equals b, right down here, I have a, I have b. Those are already in there because I ran it. So I have a, b. If I want to solve the system ax equals b, I just do x equals a backslash b. Right? So that's great. That's my solution to that matrix equation. And you can always check that, because if you take a times x, I'm hoping that I get b. Was that b? It was indeed. So that answer that I got is easily checked by taking a times x and making sure you get b. Some other fun stuff we can do here. We can create the zero matrix with this zeros command. So if I do zeros 3, 2, that makes a 3 by 2 matrix of zeros. Right? I can also make the identity matrix with the EYE, which is, I find rather odd, 3 by 3. That's the 3 by 3 identity matrix. Alright, and so here's some potential problems. Suppose I look at m and y. If I take m times y, and I just did this earlier, I get a problem, right? That's because that's because y is a row vector, right? I'm going to take a matrix and multiply it by a column vector, usually. Again, if I look at m and y, if I want to find the solution mx equals y, I would do m backslash y. But there's a problem because the dimensions must agree. This y vector must be a column, right? So I can do m backslash y transpose. The transpose turns my row vector into a column vector. And there you have it. So that's a whole bunch of things. I doubt you'll remember all of that by watching this video once, but try to remember what you can do, and then you can come back to this, to these files and see exactly how you do it, or look in the book. And there's all these commands here. But again, the most important thing with regards to Chapter 1.1 is that now we can take any system, and if it has a unique solution, we can just write it as a matrix equation and solve it very quickly, very easily with this backslash command. Alright, so that wraps up Chapter 1.2. Oh, in fact, it doesn't. I'm scrolling. Don't get dizzy here. We do have the worksheet, but again, I will save that for a third video. But for now, I think we're good. Bye.